Yeah, I just saw in the chat that the administrator said the participants are ready. So yeah, if we're okay, they can admit them in. So are you?
Please let us go.
Yeah. Okay.
Let us start.
Yeah. So hello everyone. On behalf of the Hong Kong Laureates Forum, I would like to welcome all of you to this event, Masterminds, Masterclasses, Dialogue with Young Scientists. My name is Martin Lee. I'm an associate professor at the Department of Mathematics at the Chinese University of Hong Kong, and I'm going to be the moderator for the event tonight. And tonight, we are extremely honored to have Professor Michel Talleyrand as our guest host for the section on mathematical sciences. Professor Talleyrand is Shaw Laureate in Mathematical Sciences in 2019, was a former senior researcher at the French National Center for Scientific Research in France. Professor Talleyrand has made profound contributions to probability and high-dimensional geometry, which revolutionized the mathematical research on stochastic processes, measure theory, and the mathematical theory of spin classes. Besides his fundamental breakthroughs in the frontier of research, Professor Talleyrand has also written 3 monumental and highly influential textbooks, which are now central to the work of a large number of other mathematicians. And we have a very valuable opportunity tonight to have Professor Talleyrand sharing with us his research journey and personal experience, which will certainly inspire the younger generation in the pursuit of science as their career. During this event, you are very welcome to discuss and exchange ideas freely with Professor Talleyrand. All right, so without further ado, let me, okay, so we're going to start with the first round of questions, and if time allows, we'll go with the second round. So during the first round, we can go around and for each of the participants can ask the first question. So may I ask Jimon?
Good afternoon. My name is Jimo Abdulganiyu. Mm-hmm. I am a postgraduate student, research postgraduate student at the Mohammed VI Polytechnic University in Morocco, North Africa.
Okay.
And at the School of Collective Intelligence. And I am also currently working with the Emerging Tech Foundation on machine learning, AI, data science research, but I work remotely. The foundation is in California. And that's just a brief introduction of myself. And currently, I am working on AI biases, the analysis of AI biases on facial recognition and voice recognition system. And the motivation behind this research is because of a lot of biases in AI system, AI algorithms. We are looking at how we can apply mathematical like experimental method, looking at statistics, looking at some mathematical method that we can use to make sure that how can we really evaluate if algorithm is biased, and if there should be like how it will help the economy. But currently we are still working on the research. I just started the research, I think we started in October, but we are still working on that. Currently I'm in Morocco.
Would you like to ask your question to Professor Talleyrand? Like what is you prepare the question?
You said
yeah.
His name is Professor
Talleyrand. Yeah.
Okay, Professor. Okay, thank you, Professor Talleyrand. And right, I meant to have a background in computer science, but I have a lot of interest in mathematics because of problem whereby we apply mathematical science to solve a lot of problems. Yeah, my question goes thus: why there have to be a revolution in the foundation of present mathematical analysis and set theories? Please, do you get my question?
I get your
Okay.
I understand the words, but I'm not sure what you mean.
Okay, what I mean is that why there have to be a revolution in the foundation of present mathematical analysis and set theories.
In some areas, very far from what I understand, there may be people who think they have to be a revolution, but mathematical analysis has been an established field for, say, 200 years, very solidly established field, and It works very well on a huge range of problems, and that we don't need to touch that. These theories are working very well. So for what, especially if you are interested in applying these things to practical problems like you do, I don't think there is need to go beyond what is well established now, or not, at least not anytime soon. If I understood the question correctly.
Yes, Prof. I think, like I've said before, I have background in computer science, but I happen to see this question keep coming up, like why there should be a revolution in the foundation of present.
Who said there should be a revolution? Who said there should be a revolution? That's what I'm asking, you know.
Okay,
it's not something I hear among people who do analysis. Okay. I don't think there has to be a revolution. As I said, these tools are working very well for anything you're likely to need. What is known now is more than enough. And actually, what already is known now, it takes a lifetime to learn it. You don't want to add anything to that. Okay, now for people who do extremely advanced mathematics, they may have another point of view. Okay. That's again, I heard some things which are happening in that direction. Actually, this is very far from what I do. So I learned from that in Quanta magazine. If you don't know Quanta magazine, I would really recommend to anybody to read that. It's a free online magazine which was made by the Simon Foundation, and it's really a good thing. It's a really high quality magazine, and it talks about progress in physics and biology and mathematics, and they try to explain that in general terms, which doesn't mean that some things are very difficult, and but they do a great effort for that. So it might interest everybody to look at that. And I read articles in that talking, as you say, refoundation analysis, but this is not for anything immediate. As I say, don't worry, you don't need that now. Okay, that's a clear answer for that.
That's assuring to hear that. Okay, and then maybe we move on to the next question. Let's invite Julius once to unmute yourself. Hi.
Yeah. Hello.
Hi. Hello.
I'm Julius. I'm at the moment doing my PhD at UNSW in Sydney, Australia. Really happy to join the meeting. I'm doing my PhD in theoretical physics, so I feel like that's one of the closest branches to mathematics that we have. And my question is, how did the mathematical research was impacted by the revolution of computers? So during my undergrads, I had all my analysis, algebra classes, and I barely used the computer. But now during my research, I mostly use the computer for my studies. So I was wondering how the computer affected the research in mathematics.
Of course, it depends entirely of what kind of mathematics people are doing. The way computer has the most affect my own mathematics is that it's much easier to type papers. Now, no, you don't. When I started, our group had a secretary to type papers, and they had an IBM typewriter, which has a ball. So when you type mathematical characters, you have to remove the ball which types letter and put the ball which types the Greek characters, and it's a very long process. And changes are very difficult to make. And I got hated by this good woman because I wanted to revise my papers. And now it is so easy to do that. No, it's actually, you shouldn't smile, because it makes the whole process very much easier. Now, I just finished 2 very long books. And these books, I simply could not have been written with the old system, because I revised the book. The way I proceeded is I asked people interested in the book to give me feedback. And I got hundreds and hundreds of feedback from people. And each of them I implemented it, and I improved the book, and people kept using the new version. So you think it's something given to you that proceed that way. Like, no, it's a huge improvement on what happened just 20 years ago. Okay, so that's a huge impact, because it's so much easier to work. As far as the use of computer for mathematical research, in what I'm doing, these are not used yet. But with a computer, you can experiment on computations. You can really experiment if, say, you have to study the iterates of a complicated transformation. Then you can make experiment with computers. And then once you guess a pattern on the experiment, then you can try to prove it. Okay, many people do that. Now, the impact is just starting, because now I read in Quanta magazine that there are people starting to develop formal proof systems, where the computer will help you organize proofs. Okay, but we are just at the beginning of that. It's obvious that the computer are going to entirely change the way we work and we live, but this is just the beginning of it, and it's hard to tell where it's going. No, I'm just telling you some obvious general things, because it's not I know very little about that. I'm not in contact with people who make experiments, really use the computer. But let us be prepared for that, especially the young people. Yes. What kind of physics are you studying?
I'm in cosmology, so studying. Okay. Yeah.
Okay, so I just finished my book on Introduction to Quantum Field Theory.
Okay, yeah.
Extremely great pain to do that.
Yeah, I studied quantum field theory. I took like 2 or 3 courses during my master degree, but then decided to go on the, let's say, classical path.
That was a wise decision.
It's good to hear that some confirmation on my choice.
Okay, all right. Then maybe we move on to the next participant, Kangray Park.
My name is Kangray Park, and now I am an undergraduate student in Seoul National University, and I major in mathematics. And I have lots to go to, as my dream is being a mathematician. So my question is, what abilities are needed to become a great mathematician?
This is a very good question, and of course, good questions are very difficult and don't have a simple answer. The difficult thing about being a mathematician is it is impossible to know whether you are going to be successful unless you have really tried hard to be successful. That's a sad thing, Well, okay, you can quantify that. There are very few people who are just born geniuses. And you heard Terence Tao. It's obvious that when they are your age, it's obvious that they're going to be successful. But for most of us, it's not obvious. I can tell you honestly that I have achieved in mathematics very much more than I thought it would be possible that I ever achieved when I started. Okay, especially starting in mathematics is difficult because you are confronted with people who have more experience than you have. And on a given topic, it is difficult to get to the frontier of research because there is just so much material. And one difficulty I had is when I started, I go to a seminar and then these people talk about things I don't know what it is. So I try to read the paper, and then I read the paper, and the first sentence is, "It is well known in such paper that such and such a thing happened." And of I don't know that. So I go to the paper where it said, and it starts the same thing. You know, it's well known that, and you get lost in a. Okay, so after you struggle, then you start to get a better view. But before you can really have a chance to do something, you have to invest several years of your life to master a small area. And then you have to demonstrate whether you will be able to do something new. Because sadly, you know, mathematics is not something, okay, if you don't work hard, you don't have any chance to succeed. But it's not by, if you work hard, you may not succeed. The way the mathematical process happens is somewhere deep in your brain, you know, and it's an unconscious level. I don't know what happens. Sometimes you stare at something, and you stare a long time, and then nothing happened, and then you get up the morning after, and you think there is an idea popping up in your brain. What about I try that? You know, and if this doesn't pop in your brain, then you cannot do anything. But you have to, okay, you have to invest a long time, and then you will discover whether you'll be able to do it or not. But you have to keep in mind that it also, you feel that all these people who started 10 years before you, you can never do as well as they do, but this is not true. Of course, if you work a long time, then you'll be able to do as well or maybe better than them. But that you don't know before you tried. You see, they are, okay. It's important also to understand that in mathematics, the ability of people are on very different scales. You see, it's not like when you run, you try to run 100 meters in the Olympic. You know, if you try to run 100 meters in the Olympic, 1/10 of seconds makes you a champion. But in mathematics, it's not like that. There are people who are vastly more creative than others. And okay, I will tell you, let me share with everybody the most striking experience I had in my mathematical life. Many of you must have heard of Jean Bougain. Now, Jean Bougain, who died 2 years ago, is one of the great mathematicians of the 21st and 20th century. And Jean Bougain is 2 years younger than I am. And he spent a lot of time in Paris when he was beginning. And so there was a problem which somebody asked me, and it's an exotic problem. But I worked 2 weeks very hard on that problem, and I couldn't get really anywhere. And then Jean Bougain comes to Paris, and it's lunchtime, and we say, okay, let us go to the cafeteria together. And then from our office to the cafeteria, it takes 6 minutes to walk. So I asked the problem to Jean Bougain when I left my office. And by the time we reached the cafeteria, he had solved it while walking. Okay, and I had spent 2 weeks working on that problem. So you could think that's a traumatic experience. I could have said, okay, no, I'm an idiot, you know, I cannot do mathematics. But no, this is more complicated. This was a totally exceptional person. So the lesson I drew is I cannot compete with Jean Bougain. So whenever I know Jean Bougain is working on something, I'm not going to work on that area because I don't have any chance. But the important thing is mathematics is very wide field. So you don't have to compete with the best. You have to, another way to make a progress is to look in areas where other people have not looked and make connections they have not made. And there is room for everybody. There are a few people like Jean Bougain, but not so many. And then there is room for it. So don't be, even if you meet some people who think faster than you do, or this doesn't mean there is no room for you in mathematics. It's complicated. You may be able to, of course, if you think faster than most other people, all the better. But even if you don't, you may well be qualified to become a professional. But again, that thing is like nobody can tell you now whether you will succeed or not before you have tried. Okay, you see, it's like everything in life. You have to find a balance. You have to really try hard, but also at some point, if it's not for you, it's better to recognize that it's not for you, and then don't waste the rest of your life trying something which is impossible for you. I wish there is a simple algorithm to solve all these problems, but there is not. It doesn't exist. I don't know it.
I guess that's also part of what makes it interesting. Yeah. Okay. All right. So maybe let's move on to the next question. May I invite Nan Hua?
I'm the first year PhD student of the University of Hong Kong, and good to meet you, and really nice to meet the Professor Talgret. And my question is, currently I'm doing research based on the knowledge graph, which is the graph structure, the knowledge base. And my question is, how can we better embed, do the embedding of the graph based on the structure information of the graph, like the node degree and other information? How can we do it better? Because we have so many measurements of the structure information of the graph.
Now that's a technical question about which I would have no idea, because it's a completely different area of what I'm doing. You could finish. This has nothing to do with any topic we studied, but it has. I understand this is okay. I can think of somebody who might be able to direct you on that question. This person is Asaf Naor in Princeton. Okay, because this question embedding, he had done some fantastic work on that, and he might know something more precisely. Okay, this type of question has a potential to be of considerable interest for mathematicians, because it brings new classes of problems about which they have not thought before. You see, that's the important thing, that this mathematics doesn't develop well on its own. It needs input from outside. And such a question is a beautiful type of input, from my instinct tells me. But okay, you need somebody who is in the area to help you.
Okay,
so
thank you so much.
Please try Asaf now. Yes.
Yeah, thank you so much.
All right, that's wonderful. Okay, all right. So next participant, Nan Jiang.
May I share my screen?
Sure, yeah.
Okay, thank you, Professor Lee and Professor Talleyrand. And this is Jiang Nan speaking, and I'm from Bougain University, and my major is differential equations and mathematical systems. Today, my question is whether the unbounded solution of the rational difference equations affects the bifurcation image. As we know, Stephen Wiggins gave a completed bifurcation theory of differential equations, such as fold bifurcation, flip bifurcation, Hope bifurcation of vector fields, and Neymark-Zucker bifurcation of maps. For Neymark-Zucker bifurcation, he used critical coverage to determine whether the system would have limit circles, just like the formula in this screen. But if the solution of the rational difference equation is unbounded, whether the limit circle still exists. So in 2017, Shreve and Alkali published 2 articles that the Nemack-Zucker bifurcation of a first-order difference equation and the Nemack-Zucker bifurcation of a third-order difference equation. There is an interesting phenomenon. They mentioned that unbounded solution resulted in the absence of the parabolic shape near the bifurcation value, like the figure 1 in our PowerPoint, and we can see that the orbits in the first picture are diverging like this. But this picture is the supercritical Nemack-Zucker bifurcation image. It is not consistent with our Euro image like the second picture like this. So maybe my question is a little more specific. Whether the unbounded solution of the regional difference equation affects the bifurcation image. Okay, that's all. Thank you.
Yes, probably this is a very interesting question. You have to understand it is a technical question, and probably if you ask me that question, it means that you probably don't have the right perception of how vast mathematics is. Differential equations are a very important subfield, that it's a subfield. I have done my entire life in mathematics with not knowing anything about differential equation. I had as an undergraduate, I might have met some very simple equation, and I never did that later. There are some, the amount of, you see, think the mathematics are a big globe. There are people who know, like me, who have an idea about 1% of the mathematics. Now there are people who have an idea, like Alan Koff, who probably understand 50% of the whole mathematics. And you would have to ask somebody who has studied differential equations and is doing his research in differential equations, because I can guess that this is a very difficult and elaborate question. Okay, but I love that you feel that you can pick a mathematician at random and ask him that question. No, that's not going to work. Okay, because most people know only a small area. Okay, to answer at that level of question. Now, if a high school student asks me a mathematical question, then I may have a chance to answer, because he will ask a low-level question about something I studied at university and I may remember. But a research-level question, asking at random to a mathematician, good luck. Huh? Good luck. You need to be very lucky to get an answer to that. But I saw actually, know your question is important, because again, the diagram you show with the bifurcations, I have seen that diagram, so it must be something really central. Yes. Yes. That's I can recognize that a role. Okay. Maybe that was in Quanta magazine. I don't know. Probably. So sorry, I cannot solve your problem.
Okay. Thank you very much.
All right. Thank you. So maybe we move on to the next. Tiffany Fan.
Well, hello, and it's such a great honor to be able to ask such an acclaimed professor a question. And I have yet to enter university, and on that note, I'd like to ask, given how you're publishing a book on quantum field theory, is it not essential to be specialized in physics to understand QTF, and how important is it to study math at university for physics?
I'm sorry that I didn't really understand the question, so please try again. If it's I heard the word GPS. See, that's.
I was just saying, given how you're publishing a quantum field theory book, is it not essential to be specialized in theoretical physics to understand it?
No, to understand that, I'm not specialized in theoretical physics. The reason I will tell you, the reason I wrote this book is I was very much interested in physics when I was at university. I loved it. And then I had to make a living. So at some point, about age 20, I had to choose whether I like to study math or I like to study physics. And it was a very easy choice because there were 0 positions in physics and no hope ever to get a position. And there were positions in math. So that's a very simple problem. I choose math. But then at some point I say, am I going to die without having heard of this very beautiful physics that I wanted so much to understand when I was young? And I say, okay, let me make a try to understand something for my own fun. And I read some physics and I tried to, so some physics I could understand a little bit what it is about. But then I tried to understand quantum field theory and I couldn't get a word out of it. So I really spent 10 years working very hard. And the reason I couldn't understand anything is because the physicists talk a different language than mathematicians. So there is this obstacle of language, an obstacle of way of thinking, really every line, and it's so impossibly difficult to read what they say if you are not raised like they are raised, if you are not trained like they are trained. So this particular book I wrote is because there was no book that could help me. Then I decided I will write my own book. The book I would have liked to, in which I would have liked to learn what I want to know about this topic, which is not what a physicist would do. So this is an introduction to the field written in the language of mathematicians. So if you are trained as a mathematician, you should be able to read that book. Now, it doesn't mean that it means it's trivial, because this is very non-trivial theory. There are plenty of difficult things, but at least it's written in a language you can understand. So it does not add the difficulty of the topic plus the difficulty of the language. There is only the difficulty of the topic, hopefully. The difficulty of communication between fields is a great problem, and actually probably even in mathematics, because the way different areas develop different ways to think, and it's difficult to communicate. But between math and physics, it's not difficult, it's just dramatic. It's absolutely dramatic. The work I did on spin glasses, that was absolutely, there is a book, the physicists who study spin glasses, they wrote a book which is called Spin Glass Theory and Beyond. And the book is supposed in their language to explain everything about spin glasses. And it's hardly an overstatement to say that I didn't understand a word of that book. And it's not lack of trying. I carried the book with me for a couple of years. When I was in vacation, I was reading the book on the beach when my children were playing in the water. And I really made a try, and I couldn't get a word of it because it's in a different language. And this is difficult. It's a great obstacle now to the progress of science, and there are very few people who can navigate both worlds. I could mention names, but of course there are the people who are as I said, they are. And I said for another question, there are truly exceptional people who work in science, and the rest of us cannot compete with them, but some of these exceptional people may be able to navigate between math and physics, but for the rest of us it's difficult. I'm not sure that was the right question, that I understood the question, but
yep, that completely
if I didn't answer your question, please try again.
You answered my question really well. Thank you very much.
Okay, thank you very much.
All right, thank you. So may I invite the next participant, Yang Liu?
Hi, Professor Gabriel.
Hi.
How are you today?
Oh, you have good paintings.
Yeah, I'm a university teacher from Sun Yat-sen University in China.
In China, okay.
Yeah, I think that's pretty far away from your home.
Well, I've been to China. Beside Hong Kong, I've been several times to China. Yeah.
Oh, you have been to China?
Yes.
So, which city?
Oh, I had the best trip of my life was the Silk Road.
Silk Road.
Silk Road. You start from Xi'an and move west. That was absolutely.
Oh, Xi'an. Okay, that's one of the oldest cities.
I went to Tibet also. Okay, that's great.
Yeah, so very nice to meet you.
Okay, so what's your question?
Yeah, my question is, as a teacher, I would like to know I know you are a very experienced teacher, so I would like to know how to make the learning experience of mathematics more interesting.
You see, this is a very important question. Obviously, there is no simple answer to that. If you find an answer to that, you will become very famous. People have been fighting each other on what's the best way to make students interested in mathematics. Personally, I cannot contribute to that topic because I managed not. Basically, I never taught in my life in a significant way. Only classes I taught were elementary classes in American university because I had to make a living, right? And so I really am not an expert about teaching, but I know some people who believe they are experts, and and then they disagree among each other about what should be done. So there is no, I cannot contribute to. You are right to ask this question, and I acknowledge this is a very important question, and I wish I could contribute to it. But as I said, all important question, it doesn't have any simple answer, unfortunately. Yes.
Yeah, that's a big hard question because every teacher may have different skills to put in their class and to inspire the interest of the students.
Yes.
Yeah, so maybe we can discuss it.
You have to relate.
On.
Okay, the closest I have to that experience is I was lucky that my father was a math teacher, and when I was something 13 or 14, he tried to teach me some basic group theory, and I think he did a good job because I understood what he said, but it didn't excite me so much, but it had a good positive effect. I know very little about mathematics, but basic group theory, I learned it when I was 13, and then I really understand it. So
maybe you have talent.
That's something positive.
Yeah.
But he tried to show me the group of symmetry of the triangle and the rectangle, and also I understood it, but I didn't find that so exciting. It's difficult to motivate people. Why do we do that? What's the point of doing that? It's very difficult. I understand your problem. Yes.
Okay. Thank you, Professor.
All right. Okay. So then maybe we move on to the next one. Wen Yu Du.
Hello.
Hello.
Hello. Wen Yu, right? Yeah, Professor Telegram. I'm trying to say French, like hello in French, like Wen Yu, right? I'm not sure, like to pronounce it correctly. I'm a PhD student in the University of Hong Kong. Yes. Yes. So my major is computer science, and specifically is in like the AI, machine learning and deep learning stuff, something like that. Okay. So actually, I have my original question is because it's related to the field I'm studying. Because deep learning techniques become one of the hottest topics in the last decade, right? So, but the techniques behind it still like sufficient theoretical or mathematical guarantee. It's almost like a black box.
Only thing I know about deep learning comes from Quantum Magazine.
Really?
Yes, and actually no. I wish I could understand something to that. It's a fascinating topic. It's a fascinating topic, and let us hope that in one generation, mathematics will have contributed to it. You see, because, it takes time. It takes time because again, that's a new problem. This is a new class of problem, and okay, at some point when I studied spin glasses, I heard about neural networks. I heard about something called the Hope field model. You may have learned that. But okay, this is child stuff compared to what is being done now. Okay, there's not. I cannot say anything intelligent to your question.
Okay, so
it takes. You see, you have to think on the time scale. It will take years before this thing filters to mathematicians, and whether they are able to do something or not, it will take another generation. It takes a long time. But we may hope that that's one area which will have a great impact in mathematics. Many areas had a great impact in mathematics. Theoretical physics is one of them, and now computer science is having a great impact in mathematics. I mentioned the name of Asaf now, who is an absolute star of that, and what he has done now, mathematical problems motivated by computer science, and that provided new problem. And since Asaf is basically a genius, he has done some incredible mathematical work motivated by that. So it will take time for deep learning. Let us hope that somebody here in that conference here can do something about it. Yes.
Okay. So you just said, okay, thank you so much. Like you just say some opinion from a mathematics perspective. So can I have some comments from another side, like from computer science perspective? Yes, because my original question is like, what do you think of this? Because lack of the theoretical guarantee. This is my original question. So I just changed it to a more because a lot of computer science students, because AI is so popular, a lot of students from the mathematics background that switch to start to code and start to do AI related stuff. Yes. And there is great bonus from because my undergrad and my postgrad are both from the computer science. So I really admire these students from the mathematics because they can do a lot of more theoretical stuff than us. Because we are a little bit more engineering than the science. Yes. So my question is do you think do we need to learn more mathematics? Because because I think it's quite crucial if we want to make our papers or our research more solid or stand out of the cloud.
If it was possible to know which part of mathematics you have to learn, okay? Probably there are areas like graph theory and that. But again, this is very difficult because you have this enormous mass of mathematical results, many of them very difficult and then poorly explained, and then trying to learn that it's overwhelming. It's overwhelming, So I see more chances in people already having a mathematical training. There's more chance the other way because somehow computer science is still less conceptual than mathematics. So it's probably, forgive me if I say something offending, but it's probably easier to learn some computer science when you are a mathematician than do the other way around. It's probably still easier. So that's why people now did. I don't think now can code, but he has. Okay, at least he understands the important things about computer science, and these are the kind of people who have an impact. But if you say, okay, let me learn mathematics so I improve my abilities in computer science, this looks pretty desperate, Unless there is some specific technique that you saw coming into your field, you could learn that. But otherwise, it's just finding a needle in a haystack, And, it's difficult.
Yes.
It's difficult. The odds of succeeding are small. That's what I would say.
Yes. Okay. Yes. Yes.
So, but dialogue, I would recommend dialogue with mathematicians. Instead of learning mathematics yourself, trying to communicate with mathematicians and explain your problems. That will take less effort from you, and the odds of success may be higher. But again, for the mathematician, it will be very difficult to understand the problems which are of real interest to you. That's, yeah.
Thank you so much.
Yes.
All right. Thank you. So may I ask the next one, Yundi Bunjamin?
I guess good morning, Professor Talleyrand. So I'm Yudi. I'm a PhD student in the School of Mathematics and Statistics at UNSW in Sydney. I work in design theory and combinatorics.
I love Sydney. I went twice.
Really? Well, we hope you can come soon. We hope the borders open properly soon. But my question is, we often hear people talking about mathematical problems being interesting. And I guess that seems to suggest that there are less interesting problems. And something I'm learning as a PhD student, sometimes my supervisor will say, oh, that's not a very interesting problem. So my question is, how would you describe what makes a mathematical problem interesting, especially when we talk about areas of mathematics where the applications, the real world applications may not be so apparent?
Okay. Now that's a great question. And there are several levels of answer. Now, in particular, your last sentence, applications. Applications to what? Applications to mathematics, other areas of mathematics, or applications to our daily life? You see, it would be a great mistake. It would be a terrible mistake to rate a problem as interesting only if it has application which we can witness. It changes something in the way we live. That's very short-sighted, and the important progress in science does not often come that way, by the research of a direct application. Of course, if you look for a vaccine, okay, that's something which has a direct goal, and that's very important. Okay, but the many important discoveries are not done by looking for an application. So if you want to be a mathematician, unless you are really qualified yourself as an applied mathematician, you work for a company who asks you to solve their production problem, okay, that's something respectable. But if you work just as a mathematician, what is an interesting problem? And it's a fundamental question for yourself, for your survival as a mathematician. The most difficult problem for a research mathematician is which problem should I study? See, that's a very difficult problem. So there are problems which obviously are not good. And what problem cannot be? Okay, if it's too small area, something too exotic, it's not going to be interesting. Now you try to decide some complicated object that nobody cares about. Obviously, this is not interesting. Okay, I can tell you some. My advisor, Professor Choquet, who was really a great man, he gave me this advice when he said, try to build tools. Now, this is a great advice, but this is one advice which is very difficult to apply, of course. It's how do I become a famous composer? Well, compose great music. It's the kind of advice which you don't really set out to, but you try. The way I spend a lot of time studying uninteresting problems. Okay, I have a large number of totally uninteresting papers because, okay, they solve some question about just like I said, about an object which is nobody really cares. Interesting problem has to connect, basic, concentrating on basic structure. That's what I did. Some basic, try to understand them very well. Now that's important because the basic structure will come in a lot of places. And I had my greatest success in studying, in concentrating on questions which most people would have said, no, there is really nothing to discover. here, then we know that very well for the last 50 years. But that wasn't true. You know, if you look more, you could understand something. And things are basic, very basic. Now, when I say basic structure, here's basic structure I have in mind. The sequences of 0 and 1 of length. Now, that's a very basic object. That's a very simple object. And you can do wonderful mathematics with that, which I didn't do, but some people do wonderful mathematics. Okay, so when you understand better something very basic, that's a great thing. Okay, an important problem will have consequences. It will increase your understanding of mathematics, not just answer a specific question. It will increase your understanding of mathematics. But it's difficult to tell which are the problem, and also opinions vary about that. That's another thing. You know, different people will have different opinions. So if your question, what's the interesting problem, if I have to understand the question on which problem should I work as a research mathematician, okay, I would say, well, you should not work on problems that you can obviously say are not interesting. But then the most difficult thing is you have to work on problems you have a chance to solve, or at least positive probability to solve. And I explained, don't work on a problem that Terence Tao couldn't solve. That I would advise doing that. Again, there is no algorithm, but try to use common sense to avoid the worst mistakes. That's the best I can say. In retrospect, it would be easy to make choices, but before this is difficult because one doesn't know and one is getting on. But I know myself, I wasted time on studying problems which I could tell at the time were not interesting. I should have been able to do that.
That's really great advice, yeah. So, yeah, okay.
I'm so sorry. I think my internet cut off.
Oh,
bad timing when you were answering my question. I don't know if you continue to answer.
Okay. I won't want to repeat because they will provide you the.
Yes, I thank you. I will watch the answer later. Thank you very much.
Just record it. No worries. Yeah, you can watch back later. Yeah. All right. Okay. Yeah. So maybe I also last one question. So you know, like in doing mathematical research, there are always some questions which are more like belong to the hot topics like these days, etc. Right? What would you recommend, like to like a beginning sort of researcher, just fresh PhD graduates? Do you advise them to work on sort of more popular questions, or should they try to like work on something more like people haven't looked into, as you suggest before?
Okay. Yeah. I would be very cautious about. I would not give any advice. That's a very difficult question. Again, if there's a new topic has advantages because there are some simple and important things which need not be that hard, but that simply nobody has thought about because nobody had tried the topic. So studying the topic which is just start, that might be a good idea. You have a lot of more chances to find a gold coin on the ground if it's not in a place where everybody has looked at before. But that's not the strategy I followed. You know, I followed my own taste, and I was very, in retrospect, I was extremely lucky that there were things to be done about the object in which I got interested, because some people actually sort of discouraged me to look at this kind of things. I remember, you know, when my employer had to write a research report every year, and a prominent French mathematician, he had to make a report on me on the committee, and he said, this is good mathematics, but I wish he studied something else, because he didn't believe that the kind of things I was looking at were promising. You cannot tell in advance. Now, okay, there are things you can. Now, about mathematical topics. Now, mathematical topics, they become hot. They become hot. Now they grow. There's explosive growth. They reach maturity, and when they reach maturity, most of what we have to learn from them is already. Whatever can influence the rest of mathematics goes already to the mainstream. This is already discovered. But the people who invested in these topics, they're not going to die right away, right? They spend 20 years learning that topic, and they don't want to start something else. It's too difficult, so they keep doing it. So the topic passed its prime, but it's surviving. There is a group which still does that and still publish papers. Now, I've seen many things. Now, don't get into something like that, which is past its prime. This is a dead end. You will not get anything. You will not make any important discovery. And the most favorable thing which can happen is some of these people still can help you to get a job, but you'll lead a frustrating life because your mathematics will not have any impact. So that's one thing I would say, that you should identify areas which are past and not get into them. Okay, now I will not mention any areas because
sure, yeah, of course.
Okay. No, but I did some very small areas. Okay, something I was interested for a brief time, and then I realized it's exactly what was happening. People keeping doing that. I don't know what should I do. So before getting to an area, get several advice about what people think of it. That it should not be there because it's sort of sad. It's sad.
Great. Yeah, thank you so much. It's wonderful advice. Yeah. So all right. Okay. As time is already running short, let me thank Professor Tyler Grant and all the participants again for the enlightening questions and discussions tonight. And finally, may I ask Professor Tyler Grant to just share a few words with our participants here and those who will be watching the video online, just about anything you would like to share with people.
Oh, thank you for this experience. Actually, I thought most people would be PhD students and in mathematics, and maybe I have more to tell them because, but again, these personal experience, everybody is different, and we all have to find our way. And the only advice I can give is to avoid the gross mistakes. I talked about a few of them. Maybe that's all. And keep trying. And I think after having done already worked 10 years. I was much more successful in the second decade of my works and in the first decade. So it's not because if you don't succeed right away that everything is lost. Maybe you are just not in the right direction. Again, there is no algorithm, and it all depends on each of us. I had another advice, for young mathematicians, which is a very important one actually. It doesn't work to work too hard. You have no chance if you don't work very hard. That it's not by trying to do mathematics 18 hours a day that you are going to succeed. That doesn't work that way. It's not by trying to read all the book in a superficial way that you are going to succeed. I mentioned that because one of the persons who helped me with my quantum field theory book did exactly that, and that's a terrible mistake. What you understand, you have to understand in depth. You have to understand well, because superficial understanding is not going to give you anything at all. Okay. And as far as the amount of work you have to do, your brain needs rest. now maybe I exaggerated, but not everybody can afford that. But probably every year of the last 40 years, I had 2 months vacation every year, including at least a month in summer when I was not doing any mathematics at all. And when I started doing mathematics again, I got fresh ideas, which I would not get otherwise. And now this is not my particularity. It is well known. There is a great mathematician with Hardy, the same Hardy in Littlewood. And he was working in something in the 1930s. And the way he put it there, he said, now he was British and never working on Sunday. For him, that's religious, never working on Sunday. And he was saying fresh ideas tend to come on Mondays. Your brain had a rest and then you get fresh ideas. So overworking has a negative impact on your output. You have to work hard, but you have to know the level at which you have to work. It's an individual thing, it depends for everybody. But don't think that exhausting yourself is going to bring benefits. It's not. It's like training for running. In my young days, I had the fun to run a couple of marathons, and if you overtrain, it has a negative impact. It's exactly the same in mathematics. Okay, that was my word of wisdom.
That's
enjoy
thinking. Great, yeah. Thank you so much, Professor Tyler Grant, for the precious time of sharing your personal experience in research and also many great advice and words of wisdom, which I'm sure our participants and those who are going to view the videos online would be greatly inspired. Before we end the session tonight, maybe just let me remind everyone again to stay tuned of the Hong Kong Laureate Forum website for the upcoming pre-forum events and the latest updates on the inaugural forum to be held in November 2022. All right, so thank you and looking forward to seeing you all again soon.